We've sent probes to every corner of our solar system, to the Sun, to Jupiter, even beyond Neptune's orbit. But two destinations still remain almost out of reach: Pluto and Proxima Centauri. Pluto is an icy world at the edge of sunlight, and Proxima is a star so distant that even light takes years to reach it. The problem isn't just the distance, it's the physics itself. To reach these targets, you have to travel faster than anything humanity has ever built, and then somehow slow down. That's why, even after decades of progress, both worlds remain elusive, symbols of just how vast the universe is and how small we remain within it. For decades, Pluto was an unattainable dream, a cold, silent frontier at the edge of the Sun's domain, more than 6 billion kilometers from Earth. It lies so far away that even light takes hours to cross the distance. In the 20th century, even imagining a mission there was almost like planning a journey into eternity, and yet humanity tried. In the early 1970s, NASA engineers discovered a rare celestial opportunity. Between 1976 and 1978, the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in a way that happens only once every 176 years. With perfect timing, a single spacecraft could use their gravity like a slingshot, racing through the solar system and saving decades of travel time. This concept became known as the Grand Tour, and it was meant to include Pluto. The mission design was brilliant: 4 spacecraft visiting all the major planets in one continuous journey. But the cost was astronomical. When NASA canceled the Grand Tour due to excessive expense, only 2 smaller probes survived, the ones that would later become Voyager 1 and Voyager 2. At first, Pluto was still part of the plan. NASA even considered sending Voyager 1 toward it after Saturn, but a last-minute decision changed everything. Scientists chose to redirect the spacecraft to Titan, Saturn's largest moon, a world with a thick atmosphere and potential for life. It was a scientifically sound decision, but it permanently removed Pluto from the mission. From that moment on, Pluto became the planet that kept slipping away. Throughout the 1980s and 1990s, new proposals emerged: smaller, faster probes that could reach Pluto before its fragile atmosphere froze as it moved farther from the Sun. But each time, budgets were cut, priorities shifted, and time ran out. It was too far, too slow, and too expensive. Even solar power was useless there. Sunlight was only a faint echo. Any mission to Pluto required radioisotope generators, nuclear power, and even then, energy would be scarce. Still, a few scientists refused to give up. Among them was Dr. Alan Stern, a planetary scientist who led the charge for decades. He insisted that Pluto was not just a frozen dot, but a real world that could hold secrets about the origins of the solar system. His persistence finally paid off. In 2001, NASA approved the New Horizons mission, a small nuclear-powered spacecraft built with one goal: reach Pluto before it was too late. Launched on January 19, 2006, New Horizons became one of the fastest objects ever created by humanity, accelerating to over 49,000 kilometers per hour. Even at that speed, the journey took between 9 and 12 years. When it finally arrived on July 14, 2015, it didn't stop. It couldn't. New Horizons flew past Pluto only once, performing a high-speed flyby and capturing the first, and so far only, close-up images of that distant world. For a few days, humanity witnessed what once seemed impossible: glaciers of nitrogen ice, blue hazes, and a heart-shaped plain carved into frozen terrain. And yet, even in that moment of triumph, the truth remained unchanged. The hardest part wasn't reaching Pluto. It was stopping there. When New Horizons passed Pluto in 2015, it didn't slow down. It couldn't. That single fact explains why reaching Pluto, and especially more distant worlds, is so deceptively difficult. It's not just about getting there, it's about being able to stop when you arrive. In space, speed is survival. To overcome Earth's gravity, a probe must accelerate to at least 11 kilometers per second. To reach the outer planets, even greater speeds are required, tens of thousands of kilometers per hour. But the farther a spacecraft travels, the faster it must go to avoid a journey lasting centuries, and every kilometer per second gained along the way must somehow be offset if the craft wants to slow down. That's the paradox. The faster you go, the harder it is to stop. When New Horizons left Earth, it was designed for one purpose only: a flyby. It had neither the fuel nor the propulsion system needed to enter orbit around Pluto. Doing so would have required an additional rocket stage nearly as massive as the spacecraft itself, along with decades of extra travel time. At a distance of 6 billion kilometers from the Sun, there is so little light that solar panels would barely be able to power an ordinary light bulb. And chemical fuel, used for orbital insertion near planets, becomes useless when you need to decelerate from 49,000 kilometers per hour in near weightlessness to be captured by Pluto's gravity. The spacecraft would need an engine capable of running continuously for months, along with an enormous fuel supply. Even the smallest maneuver at such a distance requires an incredible amount of energy. Every extra gram of mass adds years to the mission. So instead of trying to stop, New Horizons simply flew past, collecting as much data as it could in the few hours it had while racing at extraordinary speed. And this very problem makes Proxima Centauri even more unreachable. If the journey to Pluto took 9 years at record speed, imagine traveling to the nearest star, more than 4.24 light-years away, or roughly 40 trillion kilometers, at the speed of Voyager 1, the fastest interstellar probe ever built by humanity. Such a journey would take about 76,000 years, and even if we could accelerate to a fraction of the speed of light, we would face the same dilemma. How do you stop when you arrive? A spacecraft traveling at 10,000 kilometers per second, just 3% of the speed of light, carries kinetic energy equivalent to thousands of nuclear bombs. Slowing down from such a speed would require propulsion systems far beyond our current technology. Nuclear engines, ion drives, even advanced plasma systems like Vasimar could reduce the travel time to Proxima from millennia to centuries. But that's still not enough for a human lifetime. And every increase in speed multiplies the difficulty of braking. In interstellar space, you can't simply turn around and fire your engines. Stopping requires as much energy as starting, and most of that fuel would have to be carried from Earth. In other words, the faster you want to go, the heavier your spacecraft becomes, and the harder it is to move it at all. That's why missions like Voyager, Pioneer, and New Horizons never slow down. They are built to drift forever, carrying humanity's curiosity into the darkness. They can escape the sun's gravity, but not their own momentum. Realizing this is humbling. On the scale of the cosmos, we have taken only the smallest step. We have learned how to throw our machines into the void, but not yet how to gently stop them at another star. For now, Pluto marks the boundary of where we can reach, and Proxima Centauri remains the boundary of what we can only dream of. Humanity's path to the stars has always been defined by one word: thrust. Every leap forward, from the Moon to Pluto, has depended on how fast we can accelerate and how efficiently we can slow down. But to go beyond the solar system, we must rethink motion itself. Today, the spacecraft we launch still rely on chemical propulsion, the same basic principle used since the 1960s. It is powerful, but incredibly inefficient for deep space. To reach even 1% of the speed of light using chemical fuel, a probe would need a tank with a mass greater than that of the entire Earth. It's absurd. That's why scientists have begun to dream differently. One such idea is the ion engine, which expels charged particles at extremely high speeds. It starts slowly, but in the vacuum of space it can operate for months or even years, gradually building up velocity. Missions like Dawn have proven their reliability within the solar system, but even these futuristic engines would still take tens of thousands of years to reach Proxima Centauri. Then came Vasimer, a plasma engine developed by former astronaut Franklin Chang Diaz. Using magnetic fields to accelerate ionized gas, it promises journeys to Mars in just over a month. In theory, it could reduce interplanetary travel times by an order of magnitude, but even a perfect Vasimer-powered spacecraft would take more than 2,000 years to reach Proxima Centauri. So, engineers turned to the stars themselves, to the light they emit. Solar sails don't rely on burning fuel, but on capturing photons. Each tiny push from sunlight slowly yet steadily propels the sail forward. They are ultralight and fragile, like cosmic parachutes drifting on beams of light. In theory, they could reach another star in 1,000 or 2,000 years, still far too long for human ambition, but revolutionary. Then came a radical twist on the idea: laser sails. Instead of waiting for the sun, we could use ground-based laser arrays to accelerate a sail to incredible speeds. This gave rise to the breakthrough Starshot concept, a plan to send swarms of microprobes, each the size of a coin, to Alpha Centauri at 20% the speed of light. The journey would take just 20 to 30 years. It's bold, risky, and perhaps the first real step toward interstellar travel within our lifetime. But there's one problem. Even at those speeds, the probes won't stop. They will flash past Proxima in a matter of seconds, capture whatever they can, and vanish into eternity. The truth remains unchanged. We have mastered the art of leaving home, but not yet the science of arrival. For centuries, humanity has looked up at the night sky and seen distance as a challenge, something to overcome. From Galileo's first telescopes to the robotic eyes now wandering the darkness, our question has always been the same: how far can we go? But now, standing at the edge of what we've achieved, the answer is humbling. We can go far, but not far enough. Pluto and Proxima Centauri have become two cosmic mirrors, one at the frozen edge of sunlight, the other at a distant star. And between them lies the same barrier, the unforgiving mathematics of distance and energy. We reach Pluto through ingenuity and persistence. New Horizons revealed a world of icy mountains and heart-shaped plains, a symbol of endurance, frozen in nitrogen and methane. But even as those breathtaking images reached Earth, the probe was already racing away, silent and unstoppable, with no chance of return. It was a victory with a cost, proof that reaching the edge of the solar system is still closer to a miracle than to routine. And Proxima Centauri mocks us from beyond reach, just 4.24 light-years away, our nearest neighbor, and yet impossibly distant. At our fastest speeds, a probe would take longer to get there than the entire span of human history. Even if we could build ships capable of crossing that abyss, we would still face the same problem as New Horizons: speed without control, motion without return. Every proposed solution, fusion drives, nuclear pulse propulsion, antimatter engines, solar sails, runs into the same cosmic truth. Space is unimaginably vast. Every additional meter per second demands energy on a scale that quickly becomes impractical. And even if we solved propulsion, communication would break down, navigation would falter, and the time delays between now and then would stretch into decades. The deeper you go into space, the more alone you become. That's why missions like Breakthrough Starshot matter so much. Tiny spacecraft, lighter than a sheet of paper, accelerated by laser light. A fleet of 1,000 eyes sent into the void. They may never slow down. They may not survive the journey, but they represent something more important than success: intent, the human need to move forward even when the destination is out of reach. Because that's what exploration has always been: an act of faith. When we launched Voyager, we knew it would never return. When we launched New Horizons, we knew it would never stop. And if we ever send a mission to Proxima, we will know it won't come back to tell us what it found. But that has never stopped us. Each of these journeys is not just about science. They are about who we are. To go beyond, to reach for the impossible, is to challenge the limits built into our biology. We are creatures of gravity, bound to a single small world, but our minds refuse to stay here. We build machines as extensions of ourselves, to see, to touch, to travel where we cannot go. And perhaps one day, centuries from now, one of those machines will slow down. It will enter orbit around another star and send back images, not of home, but of another home. A pale blue dot circling a dim red sun, where the story of humanity begins again. Until then, Pluto reminds us how far we've already come, and Proxima reminds us how far we still have to go. Between them lies the truth of our era. We are explorers, confined within the slowest century of discovery, standing at the dawn of a space age we can almost touch. So we keep moving. Every launch, every failed mission, every fragment of data from a fading probe carries the same message into the stars. We are here. We are trying. And even if we are not yet capable of crossing the interstellar abyss, every light we chase brings us one step closer to what we are meant to become. Because in the end, the journey to Pluto showed us that far is just a word, and the journey to Proxima will decide whether impossible is just another meaning of it. There is something haunting about how our greatest missions end. Voyager still whispers from the darkness nearly half a century later. New Horizons drifts beyond Pluto, chasing sunlight it will never feel again. And perhaps one day, the sails of Starshot will do the same. Tiny messengers of humanity silently gliding between the stars. Each of these probes is more than metal. They are echoes of who we are: dreamers, engineers, explorers. Every signal they send is the heartbeat of Earth, a reminder that curiosity is our oldest instinct. Because the farther we travel, the more we realize space is not just a destination. It is a mirror that shows us who we are capable of becoming. When New Horizons revealed Pluto's frozen heart, it was more than science. It was a symbol. At the edge of the solar system, a heart still beats, and beyond it awaits Proxima Centauri, our nearest neighbor and our greatest temptation. 4 light years, a distance that defines the true meaning of the word impossible. And yet, we keep trying. We design faster engines, lighter sails, bolder missions, not because we expect quick success, but because hope itself demands motion. And perhaps that is the secret of our species. We are fragile, yet relentless, limited, yet unafraid of infinity. One day, our descendants will look back and see these first attempts, Voyager, Pioneer, New Horizons, as the first sparks of a cosmic dawn. They will say, that was when humanity began to expand its horizon. Because exploration has never been about escaping home. It has always been about redefining it. So we move forward, past the frozen plains of Pluto, beyond the fading light of our sun, and into the unknown between the stars. Not because it is easy, not even because it is logical, but because wonder demands it. And in that pursuit, in that endless pull forward, we discover the rarest thing of all, ourselves. And if you could choose only one destination, which would you visit first? The frozen heart of Pluto, or the unknown world of Proxima Centauri? Write your choice and your reason in the comments below. Like this video if it made you think about how far we can go. Subscribe to Hubble and join the journey beyond the known universe.